Hey class, before I get started with today's lesson, I just want to show you something on my website that you guys are going to be using for your guys' homework. So if you scroll down to today's date, I tell you on 3/24 that we have an Enthalpies of Formation worksheet, and down below I have attached Appendix C. So Appendix C, if you open it, it'll have these following big, huge numbers. What we're going to be focused on is here we have our substances. The number you're going to be focusing on for your homework are these delta H values. So I'm going to kind of talk in the lesson, when will you use these delta H values over here? Okay. So if you go down, they're in alphabetical order. I just want to tell you that. So you just have to find them. You do look in the section where you believe they will be based on their element, and then make a conscientious decision from there. So like, for example, O2, you would find the value to be 0. Okay. So let's go ahead and get onto our lesson so that makes just a little bit more sense. Today we're going to be talking about enthalpies of formation. So introduction, we used Hess's law. We calculated enthalpy changes for a lot of reactions using delta H values, but we can calculate a lot of other things, such as enthalpies of vaporization whenever we switch from a liquid to a gas. We can calculate enthalpies of fusion whenever things melt, enthalpies of combustion when things react with oxygen, etc. One of the things we're going to focus on today is enthalpies of formation. So what happens basically when products are formed? So the enthalpy change that accompanies the formation of a substance from the most stable forms of the component is known as heat of formation as well, because remember, enthalpy and heat are interchangeable. Now, the magnitude of any enthalpy change depends on temperature, pressure, state of the reactants, and products. So in order to make sure that we're using the correct values, we like to use with something called a standard state. So to compare enthalpies of different reactions, we have a defined set of conditions, that standard state. So what exactly is that standard state? Well, in order for that to be a standard state, it has to be at a pressure of 1 atm, and the temperature is 298 Kelvin, which is about 25 degrees Celsius. The standard heat of formation is denoted by a delta H, that's enthalpy. F is formation, and this little circle right here is going to be your standard. This is the change in enthalpy for a reaction that forms 1 mole of the compound with all the substances in their standard states. What that means is if they are generally a liquid at room temperature, they need to be a liquid. If they are solid at room temperature, they need to be written as a solid. If it is a gas at room temperature, it needs to be written as a gas. And these are usually written as kilojoules per mole. So when I say standard states, liquid, solid, or gas. Okay. So the standard enthalpy of formation of the most stable substance of an element is going to be 0. For example, if you have iron, Fe, and just Fe, it's 0. For carbon, the stable form is graphite. And there are 7 elements that are going to be most stable in their diatomic form. So make sure you write these down. This is H2, O2, N2, I2, Br2, F2, and Cl2. So hydrogen, oxygen, nitrogen, and your halogens. Over here, this is a standard enthalpies of formation chart. Remember, they're written as kilojoules per mole. Here we have our enthalpy, the little circle is standard, and then F is formation. This is similar to the one I just brought up right before I started this lesson. You're going to be using this chart. Here you have the substance, they have the formula, and here we have delta H. Looks a little bit different than the one you'll be using. This one only contains delta H values. So when you use the one for class, make sure you read the header and you're recording the right number. Okay. So how does this all work? Equations associated with enthalpies of formation. Here we have a question: for which of these reactions at 25 degrees Celsius does the enthalpy change represent the standard enthalpy of formation? For which it does not, what changes are needed to make the equation whose delta H is an enthalpy of formation? Well, remember, you have to meet certain criteria. One of the criteria is it has to be 1 mole of a substance. The other thing is it has to be a formation. So it has to really only have one product. And the last part is it has to be in its standard form. So what state of matter is it at room temperature? So if we look at this first one, we have 2 Na solid, 1/2 O2 gas yields Na2O solid. One thing to note is that here it meets the first criteria. It only makes 1 mole. Formation, second criteria, it's only making one product, so we're good there. And the second thing, we have to make sure everything's in its standard form. So sodium, yes, it is a solid at room temperature. And yes, oxygen is a gas at room temperature, and it's diatomic as O2. So this reaction is good. We don't have to change anything about it. So here for our second reaction, first criteria, 1 mole. Nope, it does not meet that criteria. Here we have 2. So here everything has to change to 1. This has to change to 1/2. And this has to change down to 1. Okay. Second criteria, formation of one product. Yep, we're good there. And the last one, is it in its standard form? So here, potassium is not in its standard form. If you look at the periodic table, it is a solid at room temperature. Chlorine is good, it's a gas, and KCl is good, it's a solid. Okay. And then lastly, over here, for it to reach it, does it have 1 mole as the product? No, but it also doesn't do the formation. It doesn't make one product. So actually what you need to do, is flip this equation, so then it meets both criteria. It has both 1 mole and the formation only one product. Then you check to see if everything is its standard form. Here, carbon is not in its standard form. Remember, for carbon to be in its standard form, it needs to be in graphite. Hydrogen is, and oxygen is good as well. So then that's what makes it correct. You will be doing these in your homework, but I just wanted to make sure I cover them and I kind of understand what standard form is, because you will be asked this if you guys decide to take any other chem outside of Havana High School. Let's get going into how do we use enthalpies of formation or standard of formation to calculate the enthalpies of an entire reaction. Well, we can use Hess's laws and tabulations that we know for delta H in the table that I just showed you to calculate standard enthalpy change for any reaction, as long as we know the delta H values of the reactants and products. If we're going to look, for example, at the combustion of propane, the formula is written down here. CH3, H8 gas, 5 O2 gas, 3 CO2 gas, and 4 H2O liquid. Okay. If we were going to use Hess's law, we would have to take these 3 equations and manipulate them in order to get our bottom equation. For example, here we had to flip the equation, so we got a negative. Here we had to triple the equation, which is why we got a 3. And then here we had to multiply the equation by 4, which is how we got 4. And then just like we did with Hess's law, you add them all together. As you probably noticed with Hess's law, that was a little tedious and it took a lot of brain power to make sure, hey, am I flipping this, multiplying this, cutting it in half? It took a little bit. So if we're going to walk through each of these, why they are broken down the way they do, C3H8 into graphite is a reverse. That's why I got the negative. CO2 here, there's 3 moles of it, so that's why we had to multiply it by 3. And then H2O, there's 4 moles of it, which is why we multiply it by 4. Again, that's how we got our final one. Then they have to add them all together. However, there's an easier way to calculate delta H than do Hess's law. Don't you love it when we show you the hard way and then we show you the easy way? The easy way is to actually use the following equation. So I'm going to start because please write it down. Delta H of the reaction is equal to the sum, that's what this little sigma means, the moles of your products minus the sum of the moles of your reactants. So, to break this down, N and M are the stoichiometric coefficients of each compound. It's basically the number of moles in the front of your balanced equation. So again, coefficients of balanced equation. Oh, I wrote that down there. Good. The symbol E, sigma, means the sum of, which means you are going to add them. So basically, if we were going to do the equation that they just had where they did Hess's law, one thing I want to point out is it's products minus reactants. So here we have products minus reactants. And you might be, Miss Chastain, where did they get these numbers? Well, they got these numbers from one, the balanced equation, and the second place they got these numbers is down here on the standard enthalpies of formation chart. So what they did was their products first. So here they took the coefficient and then put it down here. That's where they got the 3. Then what they did was they looked at CO2 in gas form and they looked at this chart. Here they found CO2 in gas form and they looked at the number, negative 393.5. So they plugged in negative 393.5. Here, remember, we have to sum these together. That's what the sigma meant. So here you're going to add them to the other product. So here they took the 4 and they put it right here. And then they got the negative 285.8 by looking at H2O. What is it when it's a liquid? So they found water, H2O liquid, and they saw the number was negative 285.8. Negative 285.8. So there's one set. And then they, of course, they multiplied it, got this number, multiplied it, got this number, and they added them both up to get the number right here, negative 2,323.7. For the reactant side, here they looked over here. There's one propane, so here's 1. Then they went and looked at the number for propane, C3H8. So they went down here and they found, C3H8, negative 103.85. So they plugged in negative 103.85. Then the last one, O2. O2 is in its elemental form. It is in its standard state. So it is an element is always 0. So O2, we plugged in 0. Here, they took 1 times that number plus 0, and then they subtracted those two values to get their final answer. So let's walk through our own example. Here it says calculate the standard enthalpy change for the combustion of 1 mole of benzene to form CO2 and H2O liquid. So remember, products minus reactants. So let's do our products first. Here we have 6, that's our coefficient, times, we have to look at what CO2 is. So if we look at what CO2 is, carbon dioxide, it is negative 393.5. Okay, so we times it by negative 393.5. Okay. Remember, we do the sum, so we add this to our other product. So here we do the sum of 3 times whatever H2O is a liquid is. So you look down here, H2O as a liquid is negative 285.8. So negative 285.8. Okay. Here we close that off, and then we subtract it from our reactants. So here are reactants. We only have 1 mole of that. So whatever C6H6 is as a liquid. So C6H6 as a liquid is 49. Okay, so we plug in 49. And then we add it. Here we have O2. Remember, O2 is elemental form, so that's 0. So let's go ahead and solve for this. If you do 6 times negative 393.5, you get about negative 2,361, plus 3 times negative 285.8, you get negative 857.4. When you subtract that, you get negative 3218, or when you add that, 0.4, minus the 49 we have over here, which gets you your answer of negative 3267.4. Now the unit you are going to use is kilojoules per mole, or kilojoules. Now that we've kind of walked through an example, I want you guys to try this one on your own using your table. So what I would highly suggest that you do is kind of take a picture of the table either on my classroom website, or I want you to go flip back and take a picture of this table so then you can kind of use it as you're answering this question and you have it to refer to, since you can't flip back and forth on the PowerPoint. So go ahead, take a moment, take a picture of this so that you're able to use it. So hopefully you've taken a picture. Now that you guys can go ahead, try to solve this. Let's walk through the answer. So again, here we're going to do products minus reactants. So products first. Here we have our first product. We have 2 moles of it times our CO2 value. Hopefully you guys got your CO2 value to be negative 393.5. Because if you look, your CO2 value is negative 393.5. Then you add it to your other product. So here my other product is H2O liquid. So I have a 3 times my H2O liquid. Hopefully you guys got that as negative 285.8. And then what we need to do is subtract that from our reactant. So on our reactant side, C2H5OH, that gave us the number of negative 277.7. And then we're going to add that to our O2. Since this is an element, it is going to be 0. When you go ahead and you can continue to solve, 2 times negative 393 is negative 787, plus 3 times negative 285 is 857.4. Again, this is still subtracted from negative 277.7. When you continue to add these, you get negative 1644.4 subtracted from negative 277.7. Hopefully you know when you have a negative, subtract by a negative, that becomes an addition. So that would, when you plug that into your calculator, becomes negative 1366.7 kilojoules. Wow, bad unit. Let's do that again. Kilojoules per mole. Okay. So how did you guys do? So that's the end of the lesson. Make sure that if you have any questions that you ask me and you email me. If you need help, make sure you come in before school. And I hope you guys have a good day.